And we're back with the second part of that video and finishing up this example about the Jurassic Toy Company and their stuffed dinosaurs and the volume. I wanted to show you last time just how we know we shouldn't use the actual data. You can see I graphed it here on my scatter plot on my calculator, and it's clearly not linear. I did graph the line of best fit for it, and it really isn't a best fit. So what we need to do is we need to transform the data. So if you have not already, go ahead and put your data into your calculator in list 1 and list 2. And for doing this transformation where you cube the x's, I'm going to take list 3 and tell it to be list 1 cubed. List 1 cubed. And I'm going to hit enter, and lo and behold, it gives me all of those cubed values. So now when I go to calculate my line of best fit, instead of using list 1, because that's where the x's were, I don't want the x's, I want the cubed x's, which are now living in list 3. And we're going to go to calculate, and it's going to give us our y-intercept and our slope. Instead of using x's and y's, I'm going to use the actual names of my variables so I don't get confused. We didn't do anything to the y, so it's still just volume. Remember the hat. My y-intercept here is negative 0.1039. That's sufficient. Plus, my slope is 2.3676. Sure, that looks good. Normally I would put x here, but instead of that I'm going to use scale factor. But I didn't actually use the scale factor. I used the scale factor cubed. So I'm going to write out scale factor cubed, because that's truly what's being represented there. Now the other option for transforming, again, normally you don't have to do both, but I want to show you both as an option. You can use the cube root of the y values. And why am I using cube? Because volume is measured in cubic inches, so it makes sense that it's going to be cubed. So in my calculator, to get my data, I need to go back to stat, and I need to have a new list because now I need to take the cube root of all of my y values. So under math, minus option 4, I'm doing the cube root of all the y's. The y's lived in list 2. And that gives me those values. So I can go now and do my line of best fit. I want my original x's, right, my original scale factors. But now my transformed y's, I put those in list 4. And it's going to, lo and behold, give me a new, different linear regression equation. Now again, it's no longer the volume. I did the cube root of the volume. And again, it's under a hat. Plug in your y-intercept. And your slope. And then I just left scale factor as it was, so I can just write scale factor. That didn't get cubed. Okay. Now, if you wanted to do a scatter plot of these guys to see it, you could. You do not have to. But if you want to see how it's a lot more linear now. So for instance, if I wanted to go to, go to my y equals, I'll clear out that original line. If I go to stat plot, let's see, a dot plot of my first transformation, which was when I cubed the x's, and that was in list 3. And then I also want to see, well, let's just do that one first. You can't see it there. There you go. So the blue one was the original one. Obviously, they're on different scales, but look how linear the red one is. And then if you want to do it for the other guy, we had our original x's, and then our new y's were in list 4. and we can zoom stat that. Again, you can see that. I'll turn that other one off because it's kind of messing with it. Let's turn off this guy. That's better. See, look how straight it is. Much better choice than the first one. So now that we have our different equations, we want to use the equation to predict the cubic inches of stuffing needed for a stuffed animal with a scale factor of 10. So if our x value is 10, what's going to be our predicted y hat value? I'm going to do it for both equations. This one works out a little bit nicer than the previous example, so that's why I want to show you both of them. So if you're doing it for the first transformation, where my volume is approximated by negative 0.1039 plus 2.3676, I'm going to put 10, but I need to cube it because my scale factor was cubed. So I'm going to put that in my calculator and see what it gets me. You should do this too, just to make sure you know how. Make sure I typed it incorrectly. Yep, looks good. And I get 2,367.496. Okay. 2,367.4961. I'll just write it all out. Since this is volume and it's cubic inches, I'll just do inches cubed there. Now, the next one is a little bit more complicated because we're not actually calculating the volume, we're calculating the cube root of the expected volume. So I'll show you what that means. Ooh, my hat's a little wonky. So I'll plug it in like normal. And you can do this in your calculator, and I don't need to do anything to the 10 because it was just scale factor. And I end up getting 13.31, etc. But again, that's the cube root of the volume. I don't want the cube root of the volume. I want the volume. So how to get rid of a cube root? You need to cube both sides. So I'm going to cube this, which is very easy to do. Just raise it to the third power in your calculator. And you get 2363.069. Hey, look how close it is to the last one. That's why I like this example better. It fits a little nicer. And it makes sense because we're a little bit more sure that it is actually best modeled by a cube. So 2 different answers depending on which transformation you want to use. Okay. Now, as I said before, I'm not the hugest of fans of using this because you're not always sure it's going to be a power model, or sometimes it's not a power. Sometimes it might be something different. So what happens if it's different? I'm glad you asked. Look at the next page. Like I said, this is going to be the method we'll most likely use to transform curved data into linear models. Now, even if you think it's a power model, it could be something different. Okay? But if you're thinking it's a power model, but maybe you don't know which power. Like maybe you're like, is it squared? Is it cubed? Is it to the 4th? I don't know. Is it square root? You can do logarithms. Now, I know you learned about those in pre-calculus. Luckily, you don't need to do a ton with them, but I will show you how it works. This is the general power model, right? X is raised to some power. We're going to start by taking the log of both sides. So the log of y and the log of a x to the p. And just so you know, only the x is raised to that p power, not the a times the x. Otherwise, there would be parentheses. Now, long time ago, your pre-calculus teacher taught you that when you have a product here for a log, you're allowed to separate them using addition. Right? That was a thing you were allowed to do. So using that rule, I can say, all right, I'll split this into log of a and the log of x to the p. Totally legit. You may also remember that when you have a log of some number to a power, this power is allowed to come in front of the log, right? I think it's called skipping the log, jumping the log, hopping the log, whatever analogy your teacher used. And so that p is now in front of the log of x. You don't need to put the multiplication symbol there, but I like to just so you don't think it's the word flog. It's p times the log of x. Now, if you'll notice, this kind of looks like my general formula, right? My general formula is y hat equals a plus bx. Well, I've got log of y, and then I've got log of a, and then it's p times the log of x. So let me just kind of break this down for you. This log of a, that's our y-intercept. This p, that's our slope. Okay? If you were to graph this, transform data, on your x-axis you'd have the log of your x values. On your y-axis you'd have the log of your y values. Okay? So every coordinate that's been plotted would be the log of the x values and the log of the y values. When you do this, it's going to give you a linear relationship, if in fact it's a power model. Now, if it's not a power model, it's not going to be that linear. Okay. Now, I'm using logs for this one. You can also do natural logs. It really does not matter. Now, what if it's not a power model? What if it's an exponential model? Same thing. You can use logs or natural logs. I'll use natural logs here just so you can see it, but again, it really doesn't matter which one you do. So we'll start like we did over here. We'll take the natural log of both sides. And we're going to be using the same strategy we did before. So you start by breaking it down. Oops. So you can split it by addition. And then you can split it bringing that x in front. Now this one's a little bit different because now the x is not in the log or the natural log, it's by itself. So I'm just going to rearrange it a smidge so it looks a little bit more like our equation up here. So you can see again, here is my y-intercept. And now the natural log of b is going to be my slope. So x has not been, x is not having that log or natural log applied to it. So only the y is getting transformed. So when you graph it for an exponential model, it's still your x values down here, but it's your log or your natural log on your y-axis. So every coordinate is going to be x and the natural log of y. If this is linear, then you know exponential model is going to be your best fit. Ways to remember it, I remember if it's just x, it's exponential. All right. Also, I remember it if there's double logs, that gives you more power, so maybe a power model is going to be best. So you might have to play around and see which one's going to be the better fit, the power model or the exponential model. But hopefully those two little tricks can help you remember which one goes with which. In our next video, we're going to go through an example or two, looking at power model and exponential model using logarithms.